There are two constructs in the Haskell language that allow us to introduce new data types. One is data and the other is newtype. On the surface, newtype is far more limited, right? Because you can only have a single constructor and that constructor can only have a single argument. But in turn, newtype gives you a guarantee that data doesn't give you, namely that the representation, the runtime representation of the created type is exactly the same as the runtime representation of the wrapped type. So there is no overhead. The distinction between the two types exists purely in the type checker. And that has a couple of consequences, and you could assume that basically working with new types then also means that you never pay a price. Unfortunately, that isn't necessarily the case. And in turn, though, GHC offers you some mechanisms to work with new types that you don't have in other situations. Today, we're going to look at this whole space, like how do new types compare to data? How can you coerce new types into each other? Where are the limitations of this mechanism? And yeah, other fun things.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. We've had a bit of a summer break, but we're back now. So as always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Yes. Okay, so what we see here is a simple example where I've introduced a counter new type, which is wrapping an int, right? And this is a typical situation where we might want to use something which internally we want to represent as an int, as something else. We want the representation to be the same, but we want to potentially have different operations on counter. So for example, we might want to step the counter, but we don't necessarily want to have all the other operations that we have on integer. So it definitely makes sense to wrap it up in a new type and basically thereby remove all the operations that we normally have on integers and make sure that we don't confuse other integers with counters. And just to show a little bit of the behavioral differences, I've defined two versions here. So the new type, which I think is preferable, but I've also defined counter as a data type with a slightly differently named type and constructor. And then I've defined a step counter function on both these types. And what we can do now is we can look at what GHC makes of these by compiling and looking at the core output. I have set some options up here that basically just change the nature of the core output slightly, so to suppress some information and make it more easily digestible for reading. So let's just say GHC, and then I say dedump simple, which is the typical flag we're going to use when we're interested at core output. I'm not calling it with optimizations. In this case, I just want to compile coercions.hs. And then let me show the result. And basically, we have the step counter and we have the step counter D. Let's look at step counter D first. That's the data type version. So this one goes from counter D to counter D. It takes a counter D. It does a pattern match, even at the core level, right? It unwraps the counter value, which is now called C_AZR, from the constructor, and then it reapplies the constructor to the incremented value. That's more or less what we wrote. The step counter for new types looks differently, and it's actually a little bit weird, but primarily you see there are no pattern matches, no constructor applications. Instead, there are casts. So what it does is it takes the step counter 1 RBS function, which is of type counter to int, and casts it to counter. And then this one is getting a counter value, and the counter is also cast to an integer, and then the addition is being performed. So these casts, because core still retains types, are sort of the core language's way of saying, well, actually, these things are equal or representationally equal, so I can turn them into each other, which will be a no-op at runtime, right? But we still track them at the core level because we're still interested in the types. But you can see here, okay, there is an actual pattern match and an actual constructor application for the data type, which does will be retained at runtime, whereas the casts will be dropped.
Yeah, so you can be sure that if you see a cast in core, it really will be a no-op at runtime.
Yeah,
right?
yeah.
Like there's no gotchas there, I think.
Right. So let's look at a different example, which is basically taking a list of counters and just turning it back into a list of integers. For example, I don't know, if you want to sum up all the final values of the counters or something like that. So as an intermediate step in there, you should be able to do that. And the way we would write that normally is by using map, and then we simply match on the constructor and extract. And again, we have these two versions here. So let's compile again and look at the output again. And you can see that in both cases, we have a call to map, right? And in both, like in core, we're explicit about the types. Here we're going from a list of counter to a list of int. Here we're going from a list of counter D to a list of int. And within the map here, we basically have the identity function, right? Which is cast. Whereas here we have something which is not quite the identity function, because we are, we are taking the counter D value, we're unwrapping the integer from its constructor and then returning that.
Yeah, we're doing a pattern match, right? Just like we saw in step counter
doing
D.
a pattern match. But even though we have the identity function within the map, it's not quite the same as simply having the identity function, right? Basically, because we know counter is having the same runtime representation as int, a list of counters should also have the same runtime representation as a list of int. So it should be entirely a no-op to convert from one into the other. And in a simple case like this one, you can reasonably expect GHC to perhaps be clever enough to recognize that if you enable optimizations, that it will see, oh, here we actually have map that is applied to an identity function, so perhaps I don't actually have to do this. But this is the kind of analysis which breaks down very easily on larger examples, and you cannot always rely on that. And so in general, if you have these kinds of more complicated transformations between types which are known to be runtime equivalent, you would rather guarantee by construction that they are a no-op, because
now you do have me curious though. What would happen if you enable O2?
I think it should work. I think it should work even with O1. Let me just try. As ints is as ints 1.
That's an identity, but we're still mapping as ints D.
So where are we mapping? No, and as ints we're not mapping anymore.
As ints D is still mapping.
Yeah, but
you're right. Oh, I see.
That's a data type.
Oh, yeah, right. Yeah, okay, nice. Yeah. Okay, yeah. So I did manage to get rid of the. Nice. Yeah. Okay.
I mean, here, yes, but
Yeah, in general.
I'm sorry for not coming up with a more complicated example, but I think it is relatively clear that I think even. I'm not actually sure. This is probably due to rules already. So if you write your own map function, I would be surprised if it does it, for example, right? And so there are situations where like it's very easy to see that it cannot work in general. And so in general, if you have types which you know to be representation equivalent, you would just like to guarantee that. And also, I mean, if it becomes more complicated, it is just tedious to write, right? Like, I mean, it would be easier to just say, well, it's the same. And actually, GHC allows us to do just that. Like in the case of the Newtype as ints, we can replace this call to map with a call to coerce. And coerce comes from data.coerce, which I've imported here. So you have to import that. But this type checks. And then if we do this once again, then...
Yeah, without the OZO, you've still enabled optimization.
Did I? Oh, sorry. Yeah, I should.
That was I flew you off your track.
yeah.
Sorry.
But yeah, very, very good of you to point that out. But now we see still as ints is as ints under one RCB, and that one is effectively the identity function. and it's just there's no map, right? It's just the identity function with a cast. So there's nothing, no work anymore going on. So this is very nice, right? So let's look a little bit more closely at coerce. So we can ask what is the type of coerce, and coerce has the type A to B as long as coercible of A, B holds, right? So coercible looks like a type class, and you can view it as a type class, but it's a built-in magic type class in GHC in the sense that you cannot define your own instances. If I suddenly would get the idea, well, look, I want to be able to coerce integers into Booleans, it is complaining immediately, saying that the class coercible does not support user-defined instances. You cannot define your own instances. Basically, constraints are just solved by GHC. And they are solved in simple cases, as we've already seen, like, okay, list of counter to list of int. But you can also do slightly more complicated cases. So here is a slightly more complicated example where I'm doing several Newtype induced equivalences at once. So what am I doing here? I'm going from either counter bool to either sum int. Sum int is sort of a Newtype which is defined in data.monoid, which has a different instance for like has a monoid instance, whereas normal integers don't. But is otherwise like representationally equivalent to integers. And on-off is a Newtype around Booleans, which I've been defining, and choice is a Newtype around either, which I've been defining. And like this is unwrapping the counter and rewrapping it in some int, and this is going from bool to on-off, and is going from either to choice, and all of this can just be done using coerce. And so there's basically rules in GHC that ensure that it behaves like an equivalence relation that is induced by these Newtype equivalences, so that it can be lifted through other data types, and that it's reflexive and symmetric and transitive, and that's all very nice. If I make an actual mistake, right? So for example, if I write counter D here, it will immediately complain, right? That's good, right? Because now I don't have counter D is not runtime representation equivalent to some int, and therefore the coercion should fail. So this is safe coerce, right? It's not to be confused with unsafe coerce, which also exists, but is an incredibly dangerous function, right? But like basically the point is that if you use coerce, you're not taking any risk. The compiler should only allow you to do that in situations it's considered safe. So I should also give some credit, as many things in Haskell. This also goes back to research and a paper. And I think the paper that basically talked about the introduction of these features is the Safe Zero Cost Coercions for Haskell paper by Joachim Breitner, Richard Eisenberg, Simon Peyton-Jones, and Stephanie Weyrich, which I think was at ICFP 2014, if I remember correctly. Yes, and there is a JFP version of this paper as well, which is slightly longer. But this has the general ideas. And if you want to see how this may have evolved in practice over the years, you can also look back at this paper. Okay, so one, in my opinion, incredibly useful other feature in the language where these coercions are used is what's called Newtype deriving. And actually, deriving via is yet again a generalization of Newtype deriving, which also makes use of coercions. And I'm very fond of deriving via personally.
You would have a certain bias towards that.
But even just normal generalized Newtype deriving is quite useful. And you can see that in action by, like, for example, for a counter. I just said in the beginning I wouldn't normally suggest it, but to demonstrate that you can, like if you now decide you want to treat counters as numbers after all, and for example, be able to add them and multiply them, you can derive a num instance for them, which you cannot normally do for other data types, because num is not typically a derivable class. But on newtypes, you can, with the newtype strategy, derive most classes, or basically you can try to derive all the classes that have instances for the wrapped type. And we can then call GHC with a different flag, edump deriv, to show us what's actually the generated code for the derived instance. And then it shows us that it derives an instance num counter, and it implements all the methods of the num class, plus, minus, times, negate, absignum, and from integer. And every single one of those methods is a call to coerce, right? And it's always a call to coerce. And then there are explicit type applications here, which actually make it, like, if you know what to expect, at least, make it relatively easy to read actually what's going on. Because like here we're calling coerce on eventually the plus method for integers, right? And then we're basically casting it from the type int to int to the type counter to counter to counter, which is the one that we want here. And because,
so in other words, it's precisely the same function. Yeah,
exactly. And there's no runtime overhead here. This is just type system stuff which is happening, but it is an essential use of this coercion feature.
Mm-hmm.
So this is all very nice. And basically, I mean, we could stop here. And I mean, like, this is just like, yeah, I mean, newtypes allow safe coercions. You can use them. There's the coercible class. You can use generalized newtype deriving, or even deriving via, to exploit all this. But there are some limitations, and these limitations primarily arise when you consider interactions with other features of the Haskell language, and in particular, features that go in the direction of type-level programming. And so let's assume we have a data type term, and I'm going to use so-called GADT syntax here, but I'm not yet doing anything special. So I'm just going to write a type make term is a constructor of the term data type. And so basically in GADT style syntax, if you've never seen this before, rather than just listing the constructors with their the types of their fields, you're actually just listing the type signatures of the constructors, right? The type and make term should be a constructor here that takes an A and gives us a term of A. And as is usual, when we have a data type which is parameterized, then we would expect that a term int is coercible into a term counter, right? So we should be able to go from a term int to a term counter, or the other way around, by saying coerce. And that's fine, right? Mm-hmm. But now we can do something strange. We can say, like, in our term language, we may want to treat counters like terms of type counter in a special way, namely that we are allowed to omit them. So I'm going to introduce an additional constructor omit, which doesn't take an argument, but is only of type term omit. And this is, term counter. And this is something which you cannot do with normal data types, right? So basically what this says is, if you apply the omit constructor, it doesn't give you an unconstrained term. It does give you a term of type counter. And another feature that you get from GADTs is, if you ever pattern match on a term, on an arbitrary term, and you match on the omit constructor, then you learn thereby that the type argument of the term must have been counter, right? I can show just as a simple example, if I just write term omit is omit, then the inferred type is term of counter. I won't go too much into the pattern matching aspects of GADTs here, but that's it can be quite useful, right? But we see that we now have a type error in our program all of a sudden, right? So our example term does no longer type check. Coerce is complaining, couldn't match type int with counter all of a sudden. I mean, why is that all of a sudden a problem? And it turns out that it's very, very good that GHC recognizes a problem here. Because if you consider, I mean, actually, probably I should have written the function the other way around to make the problem even more pronounced. if you consider that we would apply example term to omit, right? And omit is a term counter, and then we are coercing it into a term int, but omit is not type correct at term int, right? And so suddenly this assumption that, well, just because counter and int have the same runtime representation, term counter and term int also have to have the same runtime representation isn't true, because term counter has values with a representation which don't have a representation in term int, like in particular this omit value. And in general, this is true whenever you have type arguments in GADTs which are being constrained by some of these constructors. That is really something which is happening by name and not by representation. Like you can have a constructor that is only working for term counter, you can have another constructor that is only working for term int, and they are not exchangeable, right? And so GHC does track this, and we can actually visualize or make that more visible by asking for more information about the term data type by using the :i command. And you can see that if I ask for information on the term data type, I get the definition back, and I get the kind signature. So term is a like parameterized type from kind star to star, and I get a role annotation. And the role annotation, how do you read that? So type role is basically just the introductory form for this. Term is the name of the type that it applies to. And then it lists a role for every argument that the data type has. In this case, we have one argument A, and the role nominal applies to this argument A. So the role system is actually relatively simple in Haskell. There are only 3 roles, and I can paste them in. There is nominal, representational, and phantom. And so basically this is from most restrictive to most flexible. So what does it intuitively mean? It means that, like, if we are asking the question, can we coerce term A into term B, right? Like for types A and B, if the role of the argument of term is nominal, then we can coerce term A into term B only if the types match exactly by name, right? And that is what we currently have here. That's why we cannot coerce term counter into term int anymore. Representational is the role that we have normally, that we had before we introduced this omit constructor. The role of A would have been representational, and then you can coerce if the types, like the types that appear here, have the same representation. You can, and then this works. And there is a third role, which is phantom, which means that the types do not have to match at all. And actually, I mean, to give an example, I can awkwardly, but just for the sake of argument, slightly extend the term data type with 2 extra parameters. And I can say, well, this one is just B and C, and here I'm just taking another B and returning B and C. So the idea is the A argument is exactly the argument that we had before. So we are constraining that here in the omit constructor, and here it appears, but we are not constraining it in the second constructor. The B argument is appearing here in the make term constructor, but it is never being constrained in the result type. So it always appears unconstrained. And the C type argument is also never constrained, but it also doesn't actually appear in the type at all. There are no values of it. And if I now refresh the information, oh, sorry, I should first fix my errors. So let's actually just comment out example term for the time being as well, and then refresh the information about term. You see that now you get 3 role annotations here, and all 3 arguments indeed have different roles, right? So the first argument is the one that we had just discussed, is nominal. The second one is normal, so to speak, right? So it's like most arguments in non-GADT data types are representational. And the third argument is actually phantom. And indeed, the idea is that you can coerce phantom types in any way you like. So we could, for example, coerce a counter int bool to a counter to a term counter. So the second one is representational. We can go from int to counter here, and here we can go from, I don't know, from bool to IO unit or something like that, and that's entirely fine. Like pick a completely different type, because the type does not occur in practice, right? And so GAC keeps track of these roles for data types. One thing to consider is that if a data type is just representational, so that's the normal case. So if you, for example, define I don't know, this is a data type now, but it doesn't matter, either a and an int or something like that. So this is just a representational argument. And if I'm asking what is the info for my type, then it doesn't show a role annotation. So basically, if you don't see a role annotation in the output of GHC, then it typically means that all your arguments are representational. That's just the default. It shows it when there's something unusual going on. Nominal occurs in the situations that we have just been discussed. There is another situation which I won't go into more detail here, but I think it's relatively clear that it can lead to similar situations, namely if you're using type families. Type families are also allowing you to make distinctions based on the name of a data type. You can define a type level function that does one thing for int and another thing for counter. Right? And that means that if type families appear somewhere in other data types, then they will limit the roles of the type arguments of those data types. Right? And that is something that happens. And then generally GHC tracks this. GHC also allows you to give explicit role annotation. So if we wanted to be explicit here and document this, we could also write nominal representational phantom here ourselves, and that would be accepted as a role annotation. We can even make roles more limited. I mean, we cannot make them more liberal because that would be unsound, and suddenly we could coerce things that don't necessarily have the same runtime representation into each other. But we can restrict them, just as you can typically give type signatures which are more restrictive. You can also give role annotations that are more restrictive. And one situation in which that is, I think, often perhaps useful is in the situation where the inferred role would be phantom, because perhaps you don't actually want users to just blindly coerce. I mean, your first, like, perhaps you've introduced the phantom argument. Most likely you've introduced the phantom argument to impose some kind of typing discipline. And then you don't want someone to easily work around that by just coercing one thing into another. So it might be useful to put representational or even nominal on such a situation. And then, right, the moment I'm doing this, my example term here down here does no longer type check, because now I'm limited to this, but I could, for example, still use on/off with representational. So that would still be fine. There is one more thing to say about this. You can potentially argue that the whole thing about coercion is a little bit breaking the abstraction barrier, right? I mean, it's exposing to some extent an implementation detail, if you like, that a particular type is in fact defined as a new type. And as a library designer, you might not want to expose that fact. You might want to be able to change that decision in the future. Perhaps you've chosen this now, but you don't really want to make that part of your interface. And GHC does actually care for that by saying that these coercions for new types, they're only allowed if the constructor is actually in scope. And I can demonstrate this as well by switching to a different module. Here I'm importing the coercions module that we've just seen and data coerce, and I'm importing counter here as basically as an abstract type without its constructor. And now if I try to coerce from counter to int, it actually fails. And only if I import counter with its constructors, the coercion works.
Yeah, so
and of course, normally you would. Sorry,
you were going to say, go for it.
Go. Go.
I was just going to say, like, Anders is now choosing at the use site to import the constructor or not. Typically, this will be done in the module, right? You, as the author of the counter library, you would decide, do I want to make this exposed?
Let's do this. Or not? Let's do this properly. So let's go here, and let's say here we only want to.
Right. It's probably slightly more natural.
Export this one. Yeah, I wanted it in the other module because then I can more quickly change it. And
I can
the change matters. But from a software engineering viewpoint, it's much more beneficial to do it the other way around. Yes. Okay. There is one limitation I wanted to talk about, which is one which arises sometimes, and that is that roles don't really go very well together with higher kinds. So this is all very, very nice as long as all your arguments are parameterized by arguments. Your types are parameterized by types of kind star or kind type. But if you have higher kind of types, then things are a little bit weird. So if you, for example, consider, we know that we can, we know that we can go from a list of int to a list of counter, right? And we can do that using coerce. But could you abstract over the list here? Could you go from an f of int to an f of counter? And interestingly, you cannot. And why is that? Like, the point is, what is the kind of f here is star to star or type to type, right? But what is the role of f's argument? We don't know. We don't know what the role of f's argument is. It could be representational, and then this would be fine. But if the role of f's argument, if f is term, for example, like the original version of term that only has one argument, but that argument was nominal, then this wouldn't be sound. So it really depends on what is the instantiation of f and what is the role of that instantiation. And there is no language in GHC right now that allows us to express this. And therefore, GHC is always pessimistic and assumes that it could be instantiated. Every higher kind of thing could be instantiated to something which has role nominal arguments. And a situation where this sometimes comes back is in the case of Newtype deriving. There are some type classes which have such types, and they are difficult to derive through Newtype deriving. And just to give a small example here, I think I actually have that. Let me just check. Yeah. To give a small example here, if we define a transform class, which has a transform method, and it has such an f of a argument, and this is an argument, this f does not appear as a class parameter. This is like quantified argument, and that's the source of the problem. The class constraint and the rest doesn't really matter, right? If we do something like this, then we are in a similar situation. So I can now, for example, say I want to give an instance for transform int, and what is the thing that I would want to write here? So first of all, here I would already love to be able to just write coerce. That's the same situation that we have been up here, but I cannot, right? The only thing that I can hope to do here is fmap coerce, because I know that f must be a functor. So that's already annoying. But also, if you have an instance for transform int, you could still imagine that I can go up here again and say, just like I've been able to derive num, I should also be able to Newtype derive transform. But again, you're getting the same problem. You now have to generate an instance for transform of counter, which has to coerce these methods that involve the applications of f, and again, that is pessimistic, and there it breaks down. And there are a couple of type classes in the Haskell ecosystem that suffer from this problem as well, and are therefore, unfortunately, not easily Newtype derivable. There is some stuff, I mean, there are some libraries that help you work around this on Hackage. There is also, I think, a GHC proposal from, I think, already some years ago even, about higher order roles from 2019,
Oh, wow.
which is still open. So it's not as if, like Richard, for example, who has been working a lot on roles, it's not as if they haven't been thinking about it. In fact, I think even in the original paper, they're saying that they're citing an older paper where they're saying, like, we originally had a system which did all this, but it was far more complicated. And so they kind of deliberately made it simpler. But yeah, it would you still run into these limitations from time to time, and it's a little bit of a sad thing. But nevertheless, despite these shortcomings, I think overall coerce is extremely useful. Perhaps you're not actually using it directly all that often, although even those cases are useful. I mean, in particular, sometimes you might want to capture specific coercions, just as we're doing here, that occur very often and are sensible in the context of a particular piece of code, and just give them a different name, and that is quite a useful application. But also this, like, just that they're being sort of the core machinery being used for Newtype deriving and deriving via is, I think, just extremely useful. And knowing how the mechanism works internally helps you to understand the kind of error messages you might sometimes get. So yeah, I think that's what I wanted to tell. Are there any questions?
No questions. It's been quiet in the chat.
Do you have any
too good of a
questions?
job. No. Maybe the only thing I would add, maybe at the very end, so you understood briefly about, like, use coerce to, like, express that two things are equal, like as ints, for example, right? Just give a name to this translation. One thing I personally like doing is, I think something like as ints is fine, right? It's very clear. It's just coerced. You give the type signature, it's good. You know what's being coerced to what. I would caution a little bit against something like a larger pipeline where you have, like, a composition of functions, like you have g.coerce.f, right? Where now it's not entirely clear what the coerce is doing, right? It's taking the output of f and making it into the input of g, right? So that's, you can see it, but the types are not clear. Maybe if you refactor f, suddenly it has a different result. Maybe it's still coercible, maybe not. Maybe you get some strange error messages. Maybe you're coercing something that you didn't intend. So I feel like if you're going to use coerce in a larger composition like this, I feel it's good to give it a type signature so that you're very explicit about what is being coerced or what.
Yeah, I think it's generally also, in particular, as Etzko was saying, for the type error messages, it's often very good and sometimes even necessary to either, like, just name the function and like give it a different name and an explicit type signature, or at least, as we have seen also in the deriving output, use explicit type arguments.
Yeah, that would also
like which type you're coercing from and which type you're coercing to.
Yeah.
And I think that is typically useful, and, as I said, like, often even necessary to help GHC along. And it also will at least make the error messages much easier to understand if you are more explicit in those things. Yeah. All right.
Good.
So
thanks everyone for watching this episode of the Haskell Unfolder. It's good that we are back again. If you enjoyed it, please like and subscribe, and feel free to leave any comments below the video. We try to answer as many as we can, always. We leave the chat open for a few more minutes if you have any questions, and otherwise, see you very soon.
Yeah, and we're trying to be, we're trying to be more regular again, right? I mean, this was a longer break now, but not something that we are planning to repeat very soon. Yeah. Okay. Yeah. Bye.
I actually have no idea where I should be clicking. They changed the layout. Oh, thank you.
Okay. Bye again.